Anyone there? I'm here. Let's talk more about vectors. Alright, we've already established what a vector is. We talked about what scalars are. Now we're going to give some examples of vectors and some operations that we can do with vectors. We're going to also introduce the parallel criteria for vectors and also the dot product. So stay tuned. Alright, what is a vector? Well, remember, a vector is an object with a length and direction. As opposed to a scalar, which is a number. Notation we use for scalar, this is a review, but I just want to really hone in on this point. Notation we use for scalar is A. Sometimes we say C. Really any letter. For a vector, however, we have the arrow notation, we have the hat notation reserved for unit vectors. We have the boldface. What are some examples of scalars and vectors? Well, a scalar can represent anything really. It can represent a mass, a distance, speed, right? Like how fast am I going on the freeway? Skirt, pretty fast, 75 miles per hour. Scalars can represent temperature, energy. So associated to a scalar can be a unit, right? Like the unit of mass. A unit of mass is kilograms. A unit of distance can be centimeters, meters. A unit of speed can be kilometers per hour or miles per hour. A unit of temperature can be Celsius or Fahrenheit, etc., etc. What about vectors? How many of you know what a force is? F equals ma. This is the acceleration vector. And this is a force vector. And the mass is a scalar. We have the velocity, v. We have the angular velocity. Physics textbooks write this as omega, etc., etc. What are some operations we can do to scalars? Well, we know how to add two numbers, so like c plus d, for example. We can take two scalars and subtract them and derive another scalar. 2 minus 2 is 0, 0 is a scalar. We can multiply two scalars, for example, 2 times 2. That gives us 4, which is another scalar. We can divide two scalars, for example, 2 divided by 1 is 2, but we can't divide by 0. Yesterday we saw that we can add and subtract vectors. We also saw that we can multiply a vector by a scalar. This is called scalar multiplication. Whoa, that's an extra I. We can take two vectors and we say dot them together, and the result is a scalar. This is known as the dot product. Be mindful of the notation here. This is a dot. The dot in this context does not mean multiplication in the normal sense that we think of multiplication, like 2 times 2, for example. Multiplication of scalars gives you another scalar, but this notion of a product of vectors gives you a scalar. And we have another notion of product, which is a cross product, and that gives you a vector. The notation for that is the big X. Result is a vector. And this vector is going to be perpendicular to both the two vectors, v and w. So it would produce a new vector that's perpendicular. We'll talk about cross products later. Now, can we divide two vectors? If I have one vector, let's say 1, 2, can I divide this vector 1, 2 by another vector? Let's see about this. Well, why can we divide scalars? When we divide scalars, let's say for example 2 divided by 3, we define the operation of division to be the inverse of the multiplication operation. So this is 2 times 3 to the negative 1 power. That is the way that division is defined, as the inverse of multiplication. So if I can divide two vectors, that would mean I should have some sort of inverse operation of the dot product. Well, the dot product is not invertible, because in order for something to be invertible, it has to maintain information about the original two vectors. So when I dot two vectors, the result is a scalar. So I lose information about the direction and the length of both of those vectors. So the answer is no. No inverse of dot product. And likewise, there's no inverse of the cross product for the same reason. Therefore, there's no division of vectors. Okay. Now, how do we know if two vectors are parallel? So, parallel vectors, boop. Well, we have the parallel criteria. So we say that two vectors u and v are parallel if and only if there's some non-zero scalar such that one vector is a multiple of the other, a scalar multiple of the other. Let's think of an example. Let's think of an example. Let's take the vector 1, 2 and 2, 4. We see that 1, 2, if we take this vector 1, 2 and multiply it by some scalar 2, from last video, we learned that this is done component-wise. This is 2, 4, and this is precisely this vector. So if we label this vector v and this one u, we see that u is 2 times v, hence a scalar multiple. And if we were to draw these vectors, we'd see that they are indeed parallel. Okay, so before we finish up, let's put the notion of parallel vectors to test with this example. So here are two vectors, and they depend on some parameter t, and I want to know what values of t makes these two vectors parallel. Well, what do we know? I mean, I don't know. What does anybody know? We know that v is parallel to w if v is some scalar multiple of w. So let's exploit this fact. We know that v, I'm going to put it in component form, is 2 t squared plus 2 over 3t plus 1 t, and I want v to be equal to some scalar multiple of w, which in component form is 6, 8, 3. If you forgot how to decompose vectors and go from the decomposition vector representation and component form representation, watch that video. Alright, so now let's see if we can come up with some sort of equation that can help us determine the value of c that makes these two, the value of t that makes these two vectors parallel. Alright, well, the left-hand side and the right-hand side can only be equal if they're equal component-wise. So that sets up equations for us. The first would be that 2 is c times 6. The second is that t squared plus 2 third t plus 1 equals c times 8. And the third is that t must be equal to c times 3. Alright, So from equation 1, I see that C has to be equal to 3. Holy, 1/3, not 3. Wait, can I do algebra? I can. Okay. All right. So now let's see what C should be. All right. From this value we obtained for C, we can determine what T should be. So plugging in 1/3 for C, we get T should be equal to 1. We have 3 equations. In order for the left-hand side to be equal to the right-hand side, we need all 3 of these equations to be satisfied simultaneously. Now the first equation was satisfied easily, C equals 1/3. The third equation, we forced it to be satisfied by the constraint on equation 1. And we obtained a value for T, which was 1. And now we see if this T value will give us what we need to satisfy the equation in 2. Now notice that equation 2 is a quadratic. So in general, quadratics could have a maximum of 2 roots, which means 2 solutions, right? But equation 3 only has 1 solution because linear in T. So that means that even if we were to get solve 2 for T and we get 2 different values of T, only one of them will work to satisfy this initial equation here that I start. All right. So plugging in T equals 1 and C equals 1/3, we get this equation here. Now doing some algebra, we see that 1 plus 1 is 2, 2 plus 2/3, do some algebra, you get 8/3. Cool, satisfied. And that's an example problem of determining values that make 2 vectors